Hello and welcome to another video. In this problem, we're going to be working on minimum number of operations to make an array continuous. And so you're given an integer array nums, and in one operation, you can replace any element with nums, or in nums with any integer. And it is continuous basically if when you sort it, to make it simpler to understand, is when you sort it, all of the elements are increasing by 1, and there's nothing skipped, right? So if you sort 2, 4, 5, 3, you would get 2, 3, 4, 5, and then 1, 2, 3, 5, 6, is missing the 4, and then this is missing a lot. So it's asking for the minimum number of operations you can make to make it continuous. So if I go back here, this is already continuous, so this is fine. I can even make it a little bigger. Zoom in, there we go. So this is fine. This one, we would need a 4, so we can just change the 6 into a 4, and then that would be continuous. And this one, we'd need to pretty much change every element other than 1. So if elements are too far apart, you can kind of see here some intuition. You're never going to want to change every single element because you can always just pick an element, make it the start of a sequence, right? We can just say like, I'll just have 1, and then I can just turn everything else into what I need. So I can just make everything else into like 2, 3, 4, or the other way, if you want 1 to be the right side, you can make it like 0, -1, -2. Either one of those is fine. Now, the loophole you can get into while doing this problem, and I originally did, is try to figure out like what's the best operation. And so instead of trying to figure out what's the best operation, kind of like you want to use your intuition from the easy and medium problems where if you have a continuous sequence of numbers, you know exactly, and you know the length, you know exactly what numbers those need to be. So that's the intuition you need, right? For example, let's just say, we have 5 numbers, and we know the start is 1. So what's the end? Well, it's pretty straightforward, right? You would just do 1 plus 5. I think it would be -1. Right? So it'd be like 1 plus 5 minus 1, which would be 4. No, actually, no. In this case, it would be 5. So if you know that it starts with 1, it would be 5, right? If you know it's length 5, right? Because it would have something like this. But yeah, essentially, some basic math. If you know the length and you know the start and you know it's continuous, you can figure out like what's the range. So you can easily figure out the end number, right away. Okay. So we're going to do that for this. But there's one other issue, and the problem. So we're gonna use this intuition, right? Like we're gonna get some start number, some length, and then we are gonna figure out like what numbers are valid. But the problem is there's one other issue. Is let's say we have numbers like this: 3, 3, 5, and we figure out like, okay, well, the start is 1, let's say. And the end, what does that have to be? If it's length 5, well, it has to be 5. So what numbers are valid? And you might think like, okay, well, these are all valid. They're all in the range. But the problem is we have a duplicate. So the easy way we're going to handle duplicates is we're just going to remake this array and get rid of all duplicates. You could do this in place, but typically you don't want to modify input. So essentially what we're going to do is we are going to first get rid of duplicates, and then we're going to use these indices to figure out like, let's just get valid elements. And then if you think about it, so let's say I have an array like 1, 2, 3, 5, 6. And I know that like, okay, well, it's 5 elements. And let's say I say like, okay, well, what's an array that starts with 1 that would be contiguous? Well, it would be 1, 2, 3, 4, 5, so it would end with 5. So I know that like 4 of these are in here. Well, if you know how many elements are in your valid array, how many you have to change is just going to be n minus valid, right? And so that's the intuition we're going to use to get the solution. So instead of focusing on what's the optimal operation to make at every single point, we're just going to focus on how many of our numbers are valid, and then the changes is everything else. So you could do this a few ways. You could do a binary search, but what I'm going to do is a sliding window, which is a little bit more intuitive. So essentially what's going to happen first is we're going to take our array, and let's just get some array. Like let's say we have 1, 3, 3, 9, 9, 10 or something, 11. So let's just say we have something like this. And let's kind of walk through what we would do in this example. So first of all, we're going to want to get the length. So the length here is 7. Let's set it equal to n or something, 7. Then we're going to want to make an array without duplicates. And I forgot to mention, so we are going to want to sort it. So in this solution, like as long as the numbers are in there and they're not sorted, it's still fine. But in our solution, the way we're going to do it, either with binary search or a sliding window, you have to have sorting because then you can like figure out where stuff is really quickly. So if this wasn't sorted, we're going to sort it. It is sorted in this case. So we're going to get rid of all duplicates. So we'll have 1, 3, 9, 10, 11. And what we're going to do, it's going to be pretty straightforward. All we have to do is we're just going to take every number and make it either the left or the right bound of our solution. And then we're going to figure out like what are the bounds. And then because we're going to do sliding window, we're going to figure out like what currently is valid and what's not valid. And I'm going to kind of walk through that. But first, let's say we pick 1 as our, so we're going to have a left bound and a right bound. Let's have this be the right. And like I said, a binary search is very similar to this. You pick a bound and then you just pick like what's the index of the last element that is within bounds using a binary search, because you know you can calculate your right bound. So I'm going to show you this one, and if you want like some more work to make sure you understand this problem, you could code up the binary search approach. It's very similar to this. Okay. So let's say we pick, for every element, we're going to pick that as the right side in our example of this array. So we know the array has to have 7 elements. And what's the left bound? Well, let's actually draw this one just to figure out what's the left bound, and then we're not going to draw anymore. So this is the right, it has to be 0, -1, -2. We want 7 elements, right? So -3, -4, and we have -5. So this is a 7-element array. How do we calculate it? Well, if this is 1, so it's going to be 1 minus 7 plus 1, right? That's how you calculate the left bound. So 1 minus n plus 1, or whatever index you're on, or right minus n plus 1. This will work for everything. You can test it out. Essentially, so that's how you get the left bound. So now that we have the left bound, what can we do? So we have the left bound, which is -5, and we have 1. And so for our sliding window, there's going to be a few cases. It's either going to be all valid, or as we increase this right, because it's sorted, this left might be like too low. For example, let's say this was 30, right? And our sliding window was this. This is 30. The left would have to be like 20 something. And then this one is out of bounds. So then we would just move it up to be in bounds. And so that's kind of like our intuition for the problem. We're essentially going to move up our left to make sure that it's always in bounds. And then whatever our valid sliding window is, those are going to be all the elements that we don't need to change. And then we need to change the rest. So if we have a count, we just change n minus whatever's valid. So let's kind of walk through this. So we're going to set our result. Remember, I'm going to set it equal to 6, because worst case scenario, it will never be worse than n minus 1, because you can always just take one element and change everything else to be the numbers after it, right? So if there's 7, you're never going to need to change all 7. Worst case is going to be 6. Okay, so our bounds for this are going to be 1 and -5. So is our left in bounds? Is it between 1 and -5? Yes, it is. So this is a valid sliding window. So if this is a valid sliding window, we have one element here that we don't need to change. So how many elements do we need to change? It's going to be n minus w, where w is the length of the sliding window. And so if we need to change 1, or if we don't need to change 1, then we need to change 7 minus 1, which would be 6. So 6 and 6 is the same. Now we're going to move up our sliding window. And so here, we're going to move it up over here. And now our new sliding window is 3. And what's the left bound? So the left bound here, same thing, 3 minus 7 plus 1. So it's going to be -3. And if you think about that array, would make sense, right? It'd be 3, -2, -1, 0, and then 1, 2, 3. So that's 7 elements. That's correct. Now we check, is our left in bounds? Yes, it is. So both of these are fine as part of the valid. And if you think about it, this totally makes sense, right? Like if you draw on a -3 to 3 is a contiguous array, right? -3, -2, -1, 0, 1, 2, 3. That's contiguous. 2 of these are part of it. And so everything else needs to be changed. So if we have 2 that we don't, we need to change 5. So now we need to change 5. So now our result gets updated to 5 because that's lower. Now we go to 9. And notice how we got rid of duplicates as well by doing the set. So we're only counting each number once, because if you have a duplicate, you would always have to change the other number every time. So now we'd get this 9. So now our bounds are 9 and 9 minus 7 plus 1, which is 3. So is our left in bounds? No, it's not. So we have to move it up. And that makes sense, right? Because the array we're considering is 3 to 9. So 1 should not be in there, but 3 is fine. So we have 2 valid elements. We need to change 5 again. So that stays the same. Now we're going to move this up to 10. And so for 10, obviously this would be 10 and 4. Just they both increase by 1. This left is no longer valid, so we need to move it up. And we are going to So we have two valid elements, so we need to change 5 again, right? 7 minus 5, this problem here. So then we're going to move up our right one more time. So right is over here, left's just still over here. So for 11, it's going to be 11 and 5. 11, 5. And how many elements do we have? Well, we have 3. So we need to change 4. So 4 is less than 5. So we're going to update this to be 4. And that's pretty much it. And if you think about it, this is the optimal solution, right? So we found an array ending with 11, which would be 5. I think that's correct, right? So let's double check. So 5, 6, 7, 8, 9, 10, 11. This is what like our sliding window is representing. An array ending with 11 has 7 elements. 9, 10, 11 are part of it. So if 9, 10, 11 are part of it, we have to change this one, this one, this one, and this one. So there are 4 elements we need to change, which is correct. Okay, and so, like I said, the binary search is very similar, except for every number you pick it to be the left bound. You can pick it to be the right bound as well. So let's say you pick it to be the left bound, then you know you just need to figure out like what's the rightmost number that you can have, and then you look for what's the last number that is that, right? And that's easy to do. So like let's say I pick this to be the left bound, and I know the rightmost number I'm looking for is 11. You can definitely binary search like what's the last number that's 11 or less, have that index, get these two indices to kind of get your, it's kind of the same thing, you get your like sliding window, quote unquote, right? You get your indices of what's valid, and then you change the rest. And so for every number, you would just update this, same kind of thing. But I think sliding window is a lot more intuitive, and it's also, well, time complexity, it's not faster, but in practice, it is faster because if you think about it, sorting is n log n, but doing a binary search through every single element is n log n, while sliding window is only O of n. Even though the time complexity is still n log n because you did the sort. Okay, so now we can code it up. Also, I think sliding window is a little bit more intuitive. So we're going to have n equals length nums. We are going to make a new array here, so we can just say array equals, we're going to need to sort a set with nums. You could also just go through your nums and just take every non-duplicate and put it into a new array. That's fine too. So we do that. Then we also need to get a, which is length of array. We need to get our result. We're going to set it equal to n minus 1. You could set it equal to like infinity. It'll still work. So result equals n minus 1. And then we need the left, and that's going to be 0. And I think that's it. Okay, so now we are going to loop through the numbers. So for right in range length nums, which is n. So we are going to get this left bound. So left bound will be array of right minus n plus 1. And then while the left is too small, let's increment the left. So now we have a valid sliding window. So then we just minimize the result. Min result n minus right. So it's going to be n minus the number of valid results. So the number of valid results is right minus left plus 1, right? The length of the sliding window. So this is how many are valid, and then this is how many there are total. So we need to change n minus this. And then finally, we need to return the result. Let's try to, okay, looks like it, or let's see. We have a problem here. So index header range, let's see. Left bound equals array r. What am I doing? Oh, right. So this shouldn't loop through n. This should loop through the array. Yeah. Yeah. Because n is the length of the original array, which is how many elements you have total. But we are actually looping through our new array with no duplicates. There we go. And you can see it's a pretty efficient solution. So for the time, we did do a sort, right? So that's n log n. And then the sliding window part is O of n. And for the space, so you might be able to do this possibly without using a set. I'm not entirely sure, so if you want to try it, you can. But essentially, you can have like duplicates all over the place, and if there's a way you could figure out how to figure out like how many duplicates are in your sliding window to not count them as part of this, and then get rid of them as you get rid of them, it might be doable, but there's going to be like a lot of edge cases, I feel like. But yeah, I haven't tried it. Maybe I'll try it later. But essentially, there are going to be a lot of edge cases because you can have a bunch of duplicates of a bunch of different numbers. But there might be a way to like do it anyway, because like as you add a number, you can have like a number of how many duplicates do I have, and then the length of this would be like this minus duplicates or something like that. I'd have to try it out. But yeah, I think I'm going to stop it here. So if you did like the video, please like it. And if you want to subscribe to the channel, please do that. That really helps grow it a lot. And we're almost at 500 subs. So thanks for that one. And thanks for watching. And I'll see you in the next one.